So last time we talked about what work was. You can tell me how we calculate work. What's work?
Force times distance times cosine of the angle between.
Yep. So let's look at this problem right here. We know the force is 50. This is problem number 8 on page 69, I guess. Problem number 8. We know the force is 50 pounds. And we know we're moving the object 5 feet. So the distance is 5. And now we need the angle between those two things. So let's look at what they tell us about the force. The force is acting in the direction 2, 3. So the force is acting in this direction. Everybody agree with that? But the object is moving from the origin to a point in the first quadrant along the line y equals x. So this is the point 2, 3, and this is the line y equals x. And this would be the angle between those two, right? Would you agree with that? So you can actually find that angle in a couple of different ways. One of the ways of finding the angle would be to just think of a triangle right here. And let's look at the big angle, the force angle. This is the force angle, the big one here. Could we calculate that? Now kind of ignore that other line running up through the middle. This is 2 and this is 3. Can I calculate that right angle? How would I do that? Drew?
Second tangent, 3/2.
Yeah. So the red angle, I'll call it theta, is going to be second tangent 3/2. Now, what about the smaller angle then, the distance angle? Remember, the object is moving along this line. So could I find this angle right here? Well, I don't even really need to find it. If this is the line y equals x, how big is that? 45. So won't the angle in between those two vectors be whatever that is, minus 45? Does that make sense to you? So that's one way to do it. All right, let's figure out what that is, and we'll talk about another option you have. 7 degrees, okay. So second tangent, 3/2. I got 56.31 for that one. So I'm going to say that the angle between those two vectors, the one that I want, the little black one here, that is going to be 11.31. So in my equation, I have 50 times 5 times cosine 11.31. Is that okay with everybody? So the answer would be did you get 245.15?
Yep.
Okay. So if that way makes sense to you, then that's absolutely fine. The idea is when you calculate it, you have to know the angle between the force vector and the distance vector. And in this case, that meant doing that work. Okay? Now, let's talk about a different way to do that. What is, or what are, okay, I know the coordinates of this vector. My force vector has coordinates 2, 3. It's the direction of it. Would you agree? What about the distance vector? What are his coordinates? What are the coordinates of the distance vector? I'm just talking about his direction now. I don't know his magnitude. Actually, I do. His magnitude's 5. But what would that direction be? 1, 1, 2, 2, 3, 3. Whatever you want to pick would be the direction of that. Now, obviously, the magnitude isn't right, and the magnitude of that's not right either, but that's okay. When I'm talking about the angle, I'm only talking about the direction, right? I don't need to know how long they are. So we talked the other day that you can find the angle between 2 vectors by doing what? This is big. It's a biggie. How do we find the angle between 2 vectors? We do their dot product. So the dot product, f dot d, of these 2 vectors would be 2 times 1, 3 times 1, add them together, 5. Remember that? And then the other way of doing the dot product is to take the magnitude of the first vector, which is what? What's the magnitude of this guy? 13. Times the magnitude of this guy, root 2, times the cosine of the angle between them. Isn't this what I need right here? Yes, it is. So I'm going to figure out what that is. So 5 equals the square root of 26 cosine theta. Multiplying these 2 together, square root of 26. So 5 over root 26 is the cosine of the angle between those 2 vectors. I can call it theta for the angle between those 2 vectors. So put this right here. Instead of that, put 5 over root 26 and see what happens. See if you get the same answer. Now this one had a little round off, so it won't match exactly. But it should be really close. Is it really close? Yep. So you have an option as to how you do that, but you need the angle in between. Anybody have a question about that? Okay, all right, so that's going to be due on Tuesday. Now we're moving on to some parametric work. We actually did a little bit of this earlier in the year. And I'll be the first to admit that I don't do a lot with parametrics myself. I like to do things different ways than that, but we're going to spend a little bit of time getting some of the basics down. So, number 1 says graph this from -3 to 3 by hand. Now our calculators will do this, and we will be doing them on our calculators. But right now it says graph by hand. Does anyone have a thought how we might approach this? We have some options. Let me think of a couple of options here. Philip?
You just plug in numbers and
Okay, so they're telling us what the t-values are, right? So if we just put in, we're going to get some ordered pairs. So I'm like going to build a t-chart here. So my t-values are -3. And obviously there are numbers in between also. I'm just going to do the integers. And isn't that going to give me an x and a y? If I plug in these t's? So here we go. If I plug in -3, I get 7, -9. Keep an eye on my arithmetic. If I plug in -2, I get 2, -6, -1, -3, -2, 0, -1, 3, 2 gives me 2, 6, and 3 gives me 7. And these are ordered pairs, right? Graph and see what it looks like. So one option is exactly what Philip said, plot points. Whenever you have to graph something, you can plot points. Especially when you don't have graph paper, it's kind of, oh, I better not put arrows on the end of that either. It's kind of hard maybe to see it, but that's actually a parabola opening sideways. When we did this earlier in the year, we talked about one of the benefits of parametric equations is that you can graph things that aren't functions. That's not a function, right? So you're not going to be able to type in y equals on your calculator to graph this because it's not a function. But if you split it up and graph it parametrically, you can do it. All right, everybody okay with that? Good with that? All right, can you think of another way maybe that I could have graphed that? Robert?
Could you sub in t for the t squared?
So in other words, I could have gotten rid of the t altogether and just had an equation with x and y. So let's see, we practiced that before too. So if I do that, let's see, probably easiest to say y over 3 equals t, and then plug that in here. So x equals y over 3 squared minus 2. Let's kind of clean that up a little bit. Let's add 2 to the other side and square this. This is a little unfair because we haven't discussed all of our conic sections yet, but do you recognize that's a parabola anyway? And it's got to be sideways because we know that the up and down parabolas are y equals x squared. So when we see a y squared, we know we're going to be going sideways. This, in fact, there's no number attached to that, and if the parentheses here is x plus 2, tells me that my vertex is at -2, 0. So if you're comfortable doing that, you can absolutely do that. Now,
why wouldn't you square root y squared and then square root 9 times x plus 2?
You mean to get y by itself?
Yeah.
Well, you can, but remember when you do that, it's going to be plus or minus.
Okay.
And for most of us, it's easier to recognize what curve we're dealing with when it looks like that.
Okay.
Now, these are called the implicit functions. If you graphed y equals the positive square root and y equals the negative square root, you would get this picture.
Okay.
So you can actually graph this on your calculator, but not until you make the implicit function, see what y equals.
Okay.
Okay? Yep. Options. Options. All right, next. Now graph it on your calculator. Okay? So we're going to go to our calculator, and the first thing you're going to need to do is change into parametric mode. So go to mode, and right now you should be in function mode probably. and you're going to click over to Parametric. I think we did this earlier this year. And then for the equations, oops, I got stuff in there. If you already have equations in there, when you hit y equals, get them out. And we're going to type in x equals t squared minus 2, and y equals 3t. And then we're going to go to window, and we're going to set it up the way they told us to, which was t has to be from -3 to 3. That's their direction. Let's say that. And then, personally, I would always just start with the standard window. So -10 and 10 for y, min, and max. It looks like, since I've already built a table of values, that that's going to be fine for this problem. But sometimes it's not, and you have to make adjustments. But now when you hit graph, you should get a nice little parabola that looks like that. Okay? While I'm thinking of it, when we're messing around in parametric mode, remember that if you want to do some other stuff, you got to change back to function mode. Right? This is now in parametric mode. All right, that's easy. All right, number 3 says, do what Robert suggested for this equation, and that is change it into a Cartesian. This is called Cartesian when it's just x's and y's. So we're going to change it into a Cartesian equation. See what we've got this time with x equals 1 minus 2t and y equals 2 minus t for all t's. Okay, so what do you think we ought to do? Max, you okay? I know. Wish I could be more excited, but I'm not. Meredith, we're so happy you're here today as a senior. This is wonderful. Can you give us an idea?
Find the value of t to plug in.
Yeah, and I would probably go for this one. You could go for that one, but you're going to have to divide. So be careful. When you're solving this equation for t, if you subtract 2, that's not going to be t, that's going to be -2, or negative t, right? So I like to just move the t over here and move the y over here. Is that okay? I've got to get t. And then I'll take this guy and plug him in here. So x equals 1 minus 2 times 2 minus y. Keep an eye on my arithmetic. Is that what you got? And I went ahead and wrote it this way because when this is a line, everybody agrees it's a line, and really there's 2 acceptable ways to write lines. Y equals, or x and y on the same side. We don't really write x equals lines, so I went ahead and just changed it. This is a line. So if you graphed these, we're not going to take time to do it, but if you graphed them, you would get a line. All right, go ahead and do the next one. See what you come up with for the next one.
It's the same one.
Oh, is it the one we already did?
Yeah.
Okay, we'll cross that one off because we already did it. Let's move on to the next one. Thank you for pointing that out. I didn't even notice that. Okay, so x equals 2 cosine and y equals 2 sine. It's a little bit different. Think about this. What if I divided by 2? And for both of them. Certainly that's illegal. And now what if I squared both sides? of both equations. Well, now it would say x squared over 4 equals cosine squared, and y squared over 4 equals sine squared. Now, what would happen if I added these two equations? Just added them together. On this side, I'd have x squared over 4 plus y squared over 4. And what would I have on this side? 1. It's a circle. That's exactly right now, and this is a circle. This is the circle, x squared plus y squared equals 4. These are the parametric equations of the circle centered at the origin with a radius of 2. So if I put 3's here instead of 2's, I would have a circle centered at the origin with a radius of 3. Okay. Now the next one's a little bit different because why? Different coefficients. So let's use the same strategy and see what we come up with.
This one.
Yep.
Okay. Why can you add on that last one?
Why can you?
Yeah.
Well, if you have two equations, let's say, well, x equals y and a equals b. If these things are equal to each other and these things are equal to each other, when I add, it's adding equal things to both sides. So a and b are the same. So I could add, you would be okay if I added a to both sides of this equation?
Yeah.
Right? The addition property of equality, I can add a to both sides. B is the same thing. So b is the same thing as a. So if I add a on this side, b on this side, I've really added the same thing on both sides. Equations can always be added. So x equals 2 and y equals 5. Doesn't x plus y have to be 7? Yeah.
Yeah. Okay.
All right, so x equals 2 cosine, or no, I did that one. Y equals 5 sine. All right, so let's divide. And square. I'm doing exactly what I did last time. But it's not going to be a circle this time. When I add those this time, I am going to get x squared over 4 plus y squared over 25 equals 1. Right? Anybody know what that is? That's an ellipse. That is exactly an ellipse. See, I don't know, did you guys study the conics at all last year? The ellipse? So you know, well good, because we may not get to it this year. You know that this is centered at the origin, just like our circle was. But in the circle, the radius was 2, so we went out in 2 every direction, you know, up 2, out 2, okay? Well, this time, we're still going to go sideways 2, because the x radius is the same as it was. But now, we're going to go up and down 5, because that's the y radius. And so we end up with our nice little ellipse. Absolutely. Good work. Very, very good work. Okay, write the Write the parametric equations for the line through these 2 points. did this one already, and I erased it. What did we get as an answer when we changed it into a rectangular equation? Negative 3, I guess. Okay. I'm going to change this quickly. I'm going to change this into slope-intercept form. So it looks like the slope is 1/2. If I did my arithmetic right. Would you agree with that? Okay. And I want to look at my two equations. And I want you to understand that when you're determining values of x, you're determining them based on a t value. And when you do y, you're determining them based on a t value. And every x is changing by a multiple of -2. And every y is changing by a multiple of -1. So the ratio of the change in y over the change in x, which is slope, that ratio is -1 over -2, because this is x and y, this is y, this is x. So these numbers right here in the parametric equation, those numbers give me the slope. That's telling me how my line is moving. Does that sort of make sense to you? That when I put in a t, every t gets times by -2 for x, but only by -1 for y. So as they're marching along, the y's are changing 1, but the x's are changing 2, and that means the slope is 1/2. Now, what are these other two numbers? Well, I'd like you just to just take a look at this equation here that we got. What happens if we let x be 1? If we just plug in 1 for x, what do we get for y? 2. That's right here. So these two numbers are just a point on the line. There is nothing special about that point. They're just some point on the line. These two numbers determine the slope. Now, just be careful. X, y. Okay? So when you do slope, it's rise over run, right? So now, let's go ahead and look at the problem we're supposed to be doing, which is write the parametric equations. Write the parametric equations of the line through -2, 3, and 36. Now, because we have to do this in 3 dimensions, I'm going to show you how it's done using a vector equation first. But I just kind of walked you through how you can fill in these numbers if you want to. But let me show you how we do it in vector land. In vector land, we write a vector equation. And the vector equation looks like this. If we're in 3 dimensions, then there's 3 blanks here and 3 blanks here. And it's exactly the same idea. In the first blank goes any point on the line. Any point on the line. Well, it's easiest to use the points you've been given. So I'm going to put -2, 3. If you want to be different, you can put 3, 6. And if you want to really do work, you can try to figure out what another point on the line is. Now, this is what we call the direction vector for the line. So it tells me how the line moves. Okay, well, how does this line move? It goes from -2 to 3, that's 5, and it goes from 3 to 6, that's 3. Now, this is the vector equation. Now, again, this first thing is any point on the line, so that one or that one, totally irrelevant, any point on the line. This is how the line moves. So -2 to 3, 3 to 6. when I split this apart into two equations, x equals negative 2 plus 5t. See what I did? I took the x part of each parentheses, and then y equals 3 plus 3t. Now, remember what I told you about your parametric equation. This represents any point on the line. Does it? Yep. And this represents the slope of the line. Well, if you just went back to Algebra 1 and did slope, wouldn't you get 3 over 5? So these are the slope numbers. Remember, y over x. Now, in 3 dimensions, there is no slope. So in 3 dimensions, you're going to have to use the direction vector. Okay? All right. Okay, that was easy. All right, now, what happens in this problem if we restrict our values for t to be between 0 and 1? Now, when I wrote my equations, I really had no restrictions on t at all, so basically t could be anything. And if t can be anything, then I can generate infinitely many points, right, on this whole line going forever and ever and ever. Well, what happens if we only go from 0 to 1? Well, what do we get if we plug in 0 for t? I'm plugging it in for t now. What do I get? Negative 2, 3. All right. And what do I get if I plug in 1?
3, 6.
That's interesting. So what happens if we restrict our t values? We don't get the whole line, we just get a segment. And if we made this 0 to 2, we'd have another segment, but it'd be longer. Easy. Got it? All right, let's do a calculator problem here. See if we can figure out what's going on. Here he's walking on a horizontal line. And his distance, or the coordinates of his position, are given by this equation where t is this. Estimate the times when Gary changes direction. All right. All right, well, one way to do this is to set up a couple of parametric equations. Limits of his position given by. All right, so we're going to let he is walking on a horizontal line. So y is going to be a constant. There's nothing in the problem that clues me in, so I'm just going to pick one. Let's pick a relatively low y value and then pick. I'll pick 3. That's my horizontal line. So Gary or Larry, whoever it is out there walking along on this horizontal line. His position on that line is given by this equation. So these are going to be my parametric equations. And I'm going from 0 to 12. They tell me that. Let him walk for 12 seconds or whatever. All right, let's graph this and see what happens. So y equals, clear out the old ones, type in these new equations. By the way, the 3 was random. You can pick whatever you want. You can make it 5 or 7 or something. It won't change the answer at all. We just have to watch Larry or Gary walk on a horizontal line. So I just made this up. Okay, everybody hear me?
So could you do any number 0 through 12 and it would work still?
This is unrelated to this.
Okay.
This is just a horizontal. Think of it as a tightrope. He's walking across a tightrope, and whether it's at 6 feet or 8 feet or 20 feet, doesn't make a difference.
Okay, so
You just need to get him up off the ground.
Okay.
Okay? And then T does matter there. I gotta go from 0 to 12. I'm gonna stick with negative 10 to 10 for the other things and just see what happens. What'd you get? Did you get, I put in y equals 3, so I got the horizontal line y equals 3. Is that what you got? Okay, now hit your trace button. Did your cursor come up? Okay, when you hit trace, your cursor should have come up. Okay, I don't know what to tell you. If you put in these 2 equations, you set your t's here, and you use negative 10 to 10 for x and y, you should have exactly the same picture as I do. And when you hit trace, the cursor should pop up. Start moving your arrows and maybe you can get it on the screen. Mine popped up where t equals 0. If I look at my screen, it says t is 0, right? So x is 8.5 when t is 0. Now move your arrow buttons. And if I press my right arrow button, my cursor actually moves left, right? So Larry's moving to the left. Remember, he's on a horizontal line. So he's either moving right or left on this horizontal line. So he started at 8.5, and now he is walking left. All right, so keep pressing that cursor and watch your t values increase, right, because time is passing. And watch your x values. Keep watching them. Uh-oh, what happens? At some point, doesn't he turn around and head back the other way? I keep pressing my left arrow button, or excuse me, my right arrow button, and until I got to t equals about 5, he was moving backwards, and now all of a sudden he's moving back toward where he started. Isn't he moving right now? Okay, I can't tell what's going on. Press your right arrow button and watch the cursor go left, and then all of a sudden it starts going right. So your job in the problem was to estimate the times when Gary changes direction. So I thought it looked like around 5, when t was 5. Might be a little bit off of that. And then I don't know, does it change again?
Yeah. It's like a time.
Looks like he changes again when? Around 9. I think he changes back again around 9. He starts heading the other way.
It's like 96 when it goes from jump.
Yeah. And then he stopped when I got to 12 because I told him to. So we put in his position. This is his position equation. That was the x value because he's moving sideways. This was a random number just to get a line on there that we could watch. And then we traced his movement. And we watched him go left, and then right, and then left again. Right? Correct? All right. That probably, yeah. All right, so that's enough for today. We'll stop there. We'll pick up here next time.